Welcome to the Thompson refractor. That's the name of this massive telescope we have here. The telescope we regard as a jewel in the crown of the equatorial group, which is a group of telescopes here at Herstmonceux. The telescope has a 26-inch lens. It's not a single lens, it's a doublet. It's two lenses stuck together. They refract the light all the way down the tube from one end to the other to where we've currently got a viewfinder. The telescope and all its moving parts weigh about 12 tonnes, which is really heavy. It's as much as 2 red London buses. Now, on the other side of the telescope, where we've currently got a counterbalance weight, is where the Thompson reflector used to hang. Yes, Sir Henry Thompson actually donated 2 telescopes and not 1. It was difficult to use both telescopes, of course, at the same time while the telescope was at Greenwich. When they came here to Herstmonceux, they had more space, and the telescopes now live in separate domes. The telescope was not used to look through, although it has got an eyepiece fitted at the moment. It was actually used photographically. Now, we've got a mobile darkroom over there, and that's where the plate holders were kept. Example here. That's the black box the plate holders were held in, and that's one of the plate holders, which would actually fit on the back of the telescope for the exposure. The photographic plates themselves were developed in the main building, and they were compared. So what they would do is take photographs of the same part of the night sky, say 6 months apart, compare the two of them and measure the parallax, or the slight difference between the two pictures, to measure distances in space. Because the telescope was used photographically, to line it up, it needed a sighting scope, or a finder scope, which is on the top there. Now that's a 12.5-inch refractor. That telescope was part of the Great Equatorial, which was one of the biggest telescopes at Greenwich in the 1860s. This one was one of the biggest in the 1890s. You notice the telescopes are painted battleship grey. This is obviously strong Admiralty connection. And also, when the telescopes were moved from Greenwich to here in the 1950s, they were all taken to pieces. Now, this gave huge problems for the engineer that had to reassemble them, because there were no formal plans. These telescopes were all bespoke, all one-offs, and he had a series of postcards which they obtained from Greenwich, and he had to assemble them according to the postcards. A very difficult job. The telescope is extremely powerful. It's able to take photographs down to magnitude 19, which is very low indeed. It's 100,000 times dimmer than the faintest stars that we can see with our eyes. It was also used to measure quasars. The 26-inch lens make this telescope joint 12th largest telescope of its type in the world. Now, because of that huge lens at the top there, or huge doublet lens at the top, basically you need a very long tube in order for the telescope to offer effectively. Now, the problem with that is the telescope has a wide swing, particularly when looking at objects low in the night sky. The telescope moves around quite a bit when you're looking there or looking higher up. Therefore, it needs a rising floor, and this is one of the only ones of its kind in the world still working. The dome itself is a magnificent piece of architecture. The roof is hand-beaten Zambian copper. The walls are mahogany, possibly Cuban, very strong hardwood and extremely hard to get hold of these days, and the floor is solid teak. All of it is in fabulous condition. So what would it have been like to actually use the telescopes here in the 1950s? For a start, it would often have been really cold. The domes are deliberately designed, they're built like a fridge, and at one time apparently they even had electrically heated suits which they plugged into the walls and were left over from Bomber Command in the Second World War. Now, somebody one evening apparently smelt a strong smell of burning, wandered all round the room trying to find out what was actually on fire, and then eventually he realised it was his own Guernsey sweater, because the heated suit was actually melting on his back. The site itself is full of danger. Basically, it's not flat. Understandably, you'd normally think that when 6 telescopes are in a group, that you'll be able to walk out from a central building and walk straight paths. Not here. There are steps, there are corners, all sorts of different levels, and even a huge ornamental pond. Now, I can say without fear of contradiction that this is the only observatory in the world with a pond in it. So why did the observatory ultimately close? It's pretty obvious really when you're here these days. It's almost on sea level, there's lots of cloud, there's lots of sea mists. Although the situation, the atmosphere here was an awful lot better than London, it still wasn't very good for long-term nighttime viewing. So eventually they looked for sites elsewhere. They looked in Cape Town, they looked in South Africa, they looked in various parts of the world, and they finally settled on La Palma in the Canary Islands, Hawaii and Chile. And in each case, the telescopes these days are mounted on top of mountains or dormant volcanoes, putting the telescopes above the cloud line, and they can be used night after night after night. So finally, we've got the 12th largest telescope of its kind in the world here. This telescope was used for lunar mapping for the Apollo missions. The mapping was done here by Patrick Moore and a small team, which was sent to the Americans and formed the foundation of the maps. The telescope has a rising floor. It is a fabulous telescope to look through. I can't recommend more strongly that when you get the opportunity, when we're able to, that you come to Herstmonceux and see this telescope and the others in the equatorial group.
Hello, I'm Ian and I'm in Dome D at the Observatory Science Centre. I'm a volunteer here and this is the home of the 13-inch astrographic refractor. Now, this refractor was actually built in 1890, so as well as being the smallest telescope, it also has a great history as being one of the first telescopes to really be involved in mapping the night sky. So in 1890, this telescope was part of an 18 observatory project right around the world where they tried to map the entire sky, every star in it. Can you imagine what a task that would have been? So over 13 years, this telescope alone charted the precise positions of 179,000 stars. And, you know, without the information that telescopes like this in the late 19th century built, we really wouldn't have the star charts that we have today. The foundation of all that work was with telescopes like this. So one of the great claims to fame of this particular telescope is that in 1919, it was used to help prove Einstein's general theory of relativity. And the way it did it is the lens from this telescope was shipped all the way out to Brazil, and they took photographs of the sun in the sky at a time when the eclipse was happening. So you could actually see the stars behind the sun. And they measured precisely where those stars were. And then later, when the sun was in another part of the sky, they actually measured where the stars were then. And the difference between them measured exactly what Einstein said it would measure. So that was the first proof of that theory of relativity, which said that gravity bends light. So the sharp-eyed among you will have noticed that actually this isn't one telescope, it's two. So there's a 10-inch refractor, which just means a lens telescope on the top, and underneath we have the 13-inch refractor that the dome and the telescope's actually named after. So the 13-inch refractor was the one used for photography. And the bottom telescope is the one that actually was used in that huge sky mapping project. So the way it would work is you'd have a 6-inch glass plate attached to the end, coated in emulsion, and the telescope would actually focus on that 6-inch glass plate, and after a while, a few minutes perhaps, you'd capture the image. And then you'd put it downstairs in a dark room, somewhere where you knew it wasn't going to get light falling on it. And then at the end of the evening, the astronomer would take all the glass plates he'd used up to the main dark room in the main building and actually process them. And one day, I hope, you will be able to actually look through this telescope. The top telescope, the 10-inch one, is the one we use for, we have used for open evenings. So that is the one that we'd be looking through on a typical open evening. Although it's a 10-inch, not a 13-inch refractor, we get some fantastic views of Jupiter and Saturn and the great nebula in Orion. So if you look at the telescope, both telescopes are the same length. So they both have a focal length of 11 feet. So there's the main two barrels of the telescope here. And at the other end, and it's a wonderful masterpiece of Victorian engineering, you've got a really heavy counterweight. So the whole thing actually moves, it isn't actually all connected up now, but normally I could move it with just a touch of a finger. And it's so well balanced, thanks to the work of Howard Grubb in Dublin in the 1890s, that you can move the thing so easily across the sky. So now we're looking at the back of the telescope, and you'll notice that the whole telescope mount is angled up towards the sky, kind of a surprising angle, and that's because it's what we call an equatorial mount. And all the telescopes at the Observatory Science Centre are equatorially mounted telescopes, and it just means that basically it's angled towards the pole star, so it's parallel to the axis of the Earth, and that means that you can actually move the telescope from one side of the sky to another in just one axis. So you don't have to move it up and down, you just move it from side to side. And that's great because it means that if you've got Jupiter, for example, in the eyepiece, all you have to do is let the telescope track, and it'll track Jupiter right across the sky without, in theory, you having to do anything at all. So you remember I said earlier that this telescope was used to take lots of photographs on glass plates. Well, at the end of the evening, of course, the astronomer's job was to take all those plates up and get them processed in the main building. Now, you may have noticed, if you've been here, that it's a very strange layout, this particular site. And you've got a lily pond right outside the door downstairs in this dome. So the astronomer would come out in the evening and negotiate this lily pond. But of course, when you've been here all night, and we can't have lights, except red lights, because it destroys your night vision, then when you come out of the dome and tired, a little bit kind of sleepy, and you kind of don't really know what you're doing, perhaps, after looking through a telescope for hours on end, there's a real risk that you're going to trip up and fall in the lily pond. And in fact, quite a few astronomers did that, having finished a shift here in Dome D. And we know that because before the Observatory Science Centre opened, they dredged the lily pond outside and they found lots of old glass plates on the bottom. So we know that at least one astronomer, and perhaps many more, had ruined their entire evening's work by not remembering the lily pond. So you get the sense of what it must have been like for an astronomer. So, way into the night, they're setting up the telescope, they're sitting in their chair here and keeping an eye on the top telescope, because that tells them where they're photographing, and then the glass plate will be on the bottom one. And it's very easy in a chair like this, and although it's not the most comfortable chair I've ever sat in, it's very easy when it's late at night just to fall asleep, and that did happen. And in this particular dome, it's not a problem. But in Dome E, which I'm sure you've heard about as well, they have a moving floor. And on at least one occasion, an astronomer nearly got crushed because the floor was moving up and he was asleep in the chair and the telescope was kind of descending on him very quickly. So there was a real risk there that he was going to at least lose a few teeth. But I think he got away with it. So in this dome, I don't have the luxury of a moving floor. So we've got a piece of technology from Victorian times called a stepladder, which we use. Because if you think about it, when the telescope end is near the horizon, you're looking at something quite low in the sky, then this end is going to be quite high. So we need the stepladder to actually kind of look through the telescope. And that is basically what you'd experience if you're here on an open evening. So I hope you've enjoyed this whistle-stop tour of Dome D and the 30-inch refractor here. We hope very much to see you at the observatory very soon. Remember that there really isn't anywhere else in the UK that you can get 3 historic telescopes like this that were used by Britain's foremost observatory, the Royal Greenwich Observatory, and that are still in working order. So if you've enjoyed this video, please do go to our website and look for an opportunity to book a visit soon. Thank you.
The annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.
Hello. Anybody with even a passing knowledge of astronomy will be able to tell you about the 8 planets of our solar system. All the way from Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And I'm now going to tell you about 7 out of those 20 planets. Our first non-existent planet, our first of those mysterious 20 I mentioned, is Pluto. Now, many people still have a romantic notion that Pluto is a planet, and it's tucked out there way beyond Neptune. But Pluto is a tiny little object. Compared to our planets, minuscule. But we've discovered Makemake and Eris and Sedna and a whole load of other things, and Pluto is just one of a great many objects out there. Now, we don't want to call them all planets. For the sake of sanity, I'm afraid it was demoted to 2nd division. Pluto is a dwarf planet. Now, obviously, Pluto is still there out beyond Neptune. It hasn't stopped existing. We just stopped regarding it as a planet. And that's exactly what happened to the second of our non-planets, Ceres. The planets of the solar system: Mercury, Venus, Earth, and Mars, and then a big gap to Jupiter. Now, there is this idea of the Titus Bode law, and it spotted there was a pattern where the planets were. Now, it turns out it's just a coincidence. But because of that pattern, a lot of people were convinced there had to be another planet lying between Mars and Jupiter. And in 1801, Giuseppe Piazzi, an Italian astronomer, discovers an object lying between Mars and Jupiter. And as is the way with planets, it is named after a god. It is named Ceres for the god of agriculture, and is added to the list. A group of astronomers who were given a name, the Celestial Police, in the early 19th century were looking for this mysterious planet. And they didn't stop when they found Ceres, they carried on looking. And a year later they discovered Pallas, and they discovered Juno, and they discovered Vesta, and rapidly the number of objects dotting around between Mars and Jupiter grows and grows and grows. And just as with Pluto, we decide we cannot call them all planets, so they become known as the asteroids. Ceres is still there, not a planet, but the largest of the asteroids and the nearest of the dwarf planets. So there was no planet to be found in that position. Heinrich Olbers suggested that maybe there had been a planet there in the past. And maybe that planet had wandered too close to Jupiter. And Jupiter's gravity had torn the planet apart. And what we were seeing as the asteroids were the remnants of that ancient planet. And the planet was given the name Phaeton from mythology. And in mythology, Phaeton is the son of Helios. And he steals Helios' chariot and drives the sun across the sky for a day with chaotic results, until Zeus, who is the Greek version of Jupiter, is forced to take action and destroys Phaeton. Now, nowadays we know that even if we were to take all the asteroids and put them together, they barely come to a fraction of the size of the moon in total. There just is not enough material there to make a planet. So I'm afraid Phaeton was never a planet and must go back into the box of mythology. So it was suggested that Phaeton had been destroyed, but we now know that couldn't be the case. But other planets have been destroyed in the past. Our Earth is quite unusual because our moon is so large compared to the Earth. Now we have good evidence to believe that some 4.5 billion years ago, in the early solar system, there were more planets. And an object probably about the size of Mars has come barreling in towards the Earth, ripping away the crust of the Earth, blasting it into space. And that debris has then turned into an orbiting body that we now know as the Moon, and is slowly drifting away, even to this day, still drifting away. And we give that hypothetical planet the name Thea. Lovely name from mythology again, because in mythology, Thea was the mother of Selene, who is the goddess of the moon. The planets around our solar system are in stable orbits, but not every planet has to be in a stable orbit. Thea was a perfect example of a planet that was not in a stable orbit. It drifted, stretching its path across the solar system until it comes crashing into the early Earth. There are other planets that have been suggested in the past. One of them is the counter-Earth. And this is a wonderful idea. The idea is that we have the Earth in steady orbit around the Sun, and exactly opposite, on the far side of the Sun, is another planet, perpetually hidden from our view. Now, we do know now that can't be the case, because if it was there, an object that large, it would be unstable, and we or the Earth would be thrown out of position and we would detect it. Even if it wasn't detected from being thrown out of position, we would detect it because it would move the other planets, it would move our spacecraft. So I'm afraid the counter-Earth is also back in the box of mythology. While we're talking about gravity, let's talk about planets that do exist. Let's talk about the planet Uranus. Discovered by William Herschel, and people were able to watch its position, but they fairly soon noticed it wasn't quite where they expected it to be. It was slightly out of position. Now, a French mathematician, Urbain Le Verrier, uses the laws of gravity, and he is able to work out that there may be another planet out there somewhere, tugging it slightly out of position. And he is able to predict exactly where the planet Neptune will be found. Inspired by the success of discovering Neptune, other astronomers turn their attention to looking at the inner solar system and looking at Mercury, because Mercury was also not quite where it was expected to be. So they take the same principle and they suggest that there may be another planet lying between the Sun and Mercury. And they give this planet the name Vulcan, for the god of volcanoes. And it is imagined that this planet hugs extremely close to the Sun. It is barely more than 10 degrees away from the Sun at any time. Seeing this planet would be almost impossible. The only way people could see this planet is to watch as it crosses the disk of the Sun, or possibly to observe it in the middle of a total solar eclipse. So to hunt for Vulcan, the best opportunity was to look during a total solar eclipse. And in 1919, a total solar eclipse was observed. This telescope was one of those used to observe that eclipse, and the results are conclusive, but not for the existence of Vulcan. This telescope was used to prove Einstein's theory of relativity. And with Einstein's theory of relativity, there is a subtle change to the way that gravity works. And all those little errors in Mercury's position that people used as evidence for the existence of Vulcan disappear. And with the disappearance of that evidence, Vulcan also disappears. Einstein killed Vulcan. We are still using the same principle that Leverrier used to discover Neptune to look for more planets. Beyond Neptune lie the Kuiper belt objects, Pluto, Eris, Haumea, Makemake, all of those objects. And we can look at the orbits of those. And if those orbits are not quite where we expect, if there are unusual patterns, then maybe it indicates there is another planet somewhere out there, planet X. And astronomers have done this, and the evidence is thin, but there is some evidence that somewhere deep out in the depths of space, far, far beyond the orbit of Neptune, is another planet, perhaps 10 times the size of the Earth. Maybe so far out that it never approaches within even 100 billion kilometers of the Sun. But it could be out there. And beyond planet X, there may be other planets out there. When the planets of the solar system passed one another in the early solar system, sometimes their gravity could chaotically throw a planet, and it would be thrown way out. Planet X, lying 100 billion kilometers out from the Sun, may well be a victim of such a collision. It is also possible that when planets pass one another, they could be thrown with even greater force. It is perfectly possible there are planets out there between the stars, planets that once used to orbit a star like our Sun, and they have been thrown out, and now they are travelling detached from their parent stars, frozen cold and drifting between the stars themselves, rogue planets. We may well have had a great many more planets in the past than we currently do. Some we know about, some may be lost out in the depths. So, when an astronomer tells you about the 8 planets of our solar system, they're perfectly correct, with a few caveats. It is 8 known planets. There may be others. It's perfectly correct now. There were others in the past that we've changed our categorization on. There were others that we've imagined. And there are others that we may have lost. There are a lot of non-planets that have been and some that never were.
The annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.
Hello and welcome to the Observatory Science Centre. Mars has long fascinated people. Even ancient civilizations could look out upon the night skies and they would see Mercury and Venus hugging close to the Sun, moving very quickly around it. They could look into the depths of sky at midnight and see Jupiter and Saturn moving slowly and majestically through the night skies. But Mars moved quicker, and it was a very vibrant and noticeable red colour, and it would move obviously and quickly from one constellation of the zodiac to the next. When ancient civilizations looked for something to represent the god of war, Mars was their obvious choice. When H.G. Wells was writing The War of the Worlds and wanted a home for this alien invaded species, Mars was our obvious choice. When every B movie wanted an alien to attack us, Mars was where they came from. That fascination has remained throughout the centuries. Even in the 19th century, as science started to tackle it, that fascination was there. Percival Lovell in the 19th century used telescopes, much like this one, to study Mars. And at the eyepiece of this telescope, he would draw maps of Mars. And his imagination could see lines, and his imagination populated the surface of Mars with an ancient civilization building vast canals to carry water from its poles across a dying and drying planet to feed the people. And into the 20th century, and even in the 20th century, that fascination remains. In the mid-20th century, people such as Patrick Moore, for example, would still talk about life on Mars, almost as though it was a certainty. But then in 1969, Mariner 4 travels to Mars, and it is able to send us the first photographs. And it shows that the surface of Mars is in fact a cratered and blasted surface, more akin to the Moon and the Earth. And with those photographs, any imaginations, any dreams of life upon Mars evaporated, just like the waters upon Mars from Lovell's canals. Let's compare the Earth and Mars. This is our home, the Earth. Our globe, about 13,000 kilometers across. Our globe surrounded by the thinnest of layers of air and water, a thin layer that is all that separates life upon the Earth from the freezing, dead, desolate regions of space. And this is Mars. It's about half the size of the Earth, over 6,000 kilometres across. It's about half the gravity. Unable to hold on to its water because that gravity is so low. Unable to hold on to that air. So unlike the Earth, with its thin protective layer of atmosphere, Mars has lost that air, and the waters have boiled away into space. So while Mars and Earth are very similar in some ways, Mars is indeed the most Earth-like planet. Mars has frozen and dried. Life on Mars? Certainly not on the surface. You may have noticed that it's open season on Mars now. A lot of spacecraft being launched towards Mars. At the moment, Mars is only 80 million kilometers away from the Earth. And that has absolutely nothing to do with why spacecraft are going to Mars now. For example, NASA's Perseverance spacecraft is currently heading towards Mars. It is not going to travel 80 million kilometers towards the Earth. If that spacecraft travelled straight towards Mars, travelling 80 million kilometers, then by the time it has travelled that 80 million kilometers, Mars will no longer be there. That journey, travelling that direction, is much longer. But because our spacecraft travels in the same direction that the Earth did, because our spacecraft travels in the same direction that Mars is, it actually takes a lot less fuel. And if our spacecraft can carry a lot less fuel, we can carry a lot more science. We take that route, NASA takes that route, the UAE take that route, Russia take that route, because it is the most fuel efficient route. And that's why it's open season on Mars. Those spacecraft take a long curving path that travels 500 million kilometers. And in 9 months, our spacecraft will be on the far side of the Sun. In 9 months, Mars will be on the far side of the Sun, and they will meet up again. Currently, there are 3 major missions on their way to Mars. Missions from NASA, a mission from the United Arab Emirates, and a mission from Russia. And the biggest of them is NASA's Perseverance rover. It's a craft that is very similar to the Curiosity rover. This is a robot that is about the size of a small car. It's got a mass of about a ton. And that raises a question. How do you get something that massive safely onto the size of Mars, onto a planet like Mars? We can't use parachutes all the way down because the air is so thin. Parachutes won't work. We can't use rockets because if you use rockets, then the exhaust from the rockets will blow so much debris that it would damage our own robots. We can't, as some smaller robots do, use airbags and bounce down onto the surface because with a ton-sized craft, you're just going to break it. So how do we do this? What we do is we embark upon something that was colloquially known as 7 minutes of terror. As the robot enters the thin and tenuous atmosphere of Mars, it uses air braking, just like spacecraft returning to the Earth. And that will slow it down. Not very much, because the air is so thin, but it will slow it down from 20,000 kilometers an hour to 2,000 kilometers an hour. Cannot land that fast, you'll be a crater. So at this point, we do use parachutes. But parachutes don't work very well in such a thin air. Well, they'll slow it down a little bit. So they slow it down from perhaps 2,000 kilometers an hour to maybe 200 kilometers an hour. And then the parachutes won't work any longer. You still cannot land at that speed. If you land at 200 kilometers an hour, you will be a pile of rubble. So then what we do is something which is quite ingenious. The rockets come down, the spacecraft comes down, and then it fires rockets, and it will hover above the ground. And when it is hovering about 20 meters above the ground, it lowers the robot on cables. So the robot touches the ground and the rocket flies away. So if the Perseverance robot is so similar to Curiosity, why is it going there? Well, Mars is very similar to the Earth, as you said, but with no atmosphere and no water that we can be aware of upon its surface. But we do know there is evidence of water. Robots, like Curiosity, travelling across the surface of ancient basins, have discovered clays and gravels, rocks that can only be formed underneath water. Spacecraft like the Phoenix lander have seen evidence of ice water settling upon the poles of Mars. And spacecraft in orbit around Mars have been able to stare through the icy surface of its poles and discover evidence of liquid water beneath those poles. There is evidence of liquid water upon the surface of Mars. Perseverance will land in an area upon Mars that is known as the Jezero crater. The Jezero crater is an area that we believe was flooded long, long ago. It shows evidence of vast river valleys flooding into that area and having laid down vast amounts of sediment in an ancient river delta. Perseverance will have a much more sophisticated set of tools to investigate Mars than Curiosity did. One of the things it will have is a drill that will allow it to drill below the surface and look amongst the sediment and the rocks of those ancient river deltas. Now, Mars on a nice summer's day might be minus 20 centigrade. On a cold winter's night, it could dip down to minus 140 centigrade. It has barely any air, so the surface is bombarded by radiation from the sun. It has no magnetic field, so there's nothing to shield. If there is any life upon Mars, we are not going to find it upon the freeze-dried, radiation-baked, frozen surface. It will be below the ground, under the surface. And that is what we want to do. We want to look for life and the evidence of life in those ancient riverbeds. Modern robots, such as Perseverance, used in spaceflight, depend a lot on artificial intelligence because it's so far away that if it needs to ask for help, it could be half an hour before it gets a reply to saying help. So it has to make decisions on itself. And good as they are not that good. It has been said that a robot investigating geology for a week is outperformed by one person with a hammer in 10 minutes. So one of the things that Perseverance is going to do is it is going to take samples with that drill and it will store the samples inside the body of the spacecraft. So those samples could be returned to Earth at a later date where we'll be able to study them in far more detail. And finally, one piece of technology that Perseverance will carry with it is in the belly of the robot. It's going to carry a little drone helicopter. Now, the air on Mars is incredibly thin, but with good engineering and very lightweight materials, it's possible to make a little helicopter that can fly, controlled by artificial intelligence, and it would be able to fly through the skies of Mars, and our robot can see over the next hill. Now, there's a couple of reasons for doing this, a couple of good reasons. One is that it's a technology demonstrator to test for particular technologies that we might use on future missions. Another one is that it allows our robot to see over the next hill and plan its next move. But let's be honest, the best reason has got to be, this is so cool. If you could go flying helicopters through the skies of Mars, wouldn't you? Of all the planets in our solar system, Mars is a planet that is thought most likely to harbour life, most likely to have harboured life in the past. And over the history of science, opinion has swung from the 19th century, when people were convinced that life on Mars was an absolute certainty. We move into the 20th century, and that conviction of life upon Mars has been reduced to a B-movie fantasy. But now, opinion's moving back, because we've discovered life is far more tenacious than we thought. We have found life in ice core samples from the Antarctic, where the temperatures are colder than those on Mars. We have found life in the rocks themselves upon the Earth. So digging for life on Mars is not unreasonable. We have found life that can survive being exposed to a vacuum, freeze-dried, warmed up again, rehydrated, and it comes back to life. We have even found life that is quite happy staying alive, living inside the cores of nuclear reactors. So the idea of taking an environment like Mars, minus 140 centigrade, radiation, these are not problems for life as we understand it. We just need to go and look. And that tenacity of life gives us one big problem. In all of these missions that we send to Mars, biosecurity, lovely word, biosecurity is a major concern. H.G. Wells wrote in the 19th century, The War of the Worlds. And in the War of the Worlds, the alien invaders are wiped out by the microbial life upon the Earth. And we are very careful when we send these spaceships to Mars and other planets and moons to make sure they are sterilised, so we don't accidentally carry Earth's microbial life to Mars, where we might end up being the alien invaders, wiping out the environment we want to study.
The annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.
Hello and welcome to Herstmonceux Observatory. My name's Jen, and today we're going to be talking about spaceports, satellites and thermal imaging. So in the UK we actually have 7 spaceports, and we send little satellites into space. Some of them we launch off of rockets, so big rockets like you've seen on TV. Others go up on aeroplanes, so the aeroplanes take them some of the way up and then they go off into space from the aeroplane. The horizontal launches are the ones off the back of aeroplanes, and they're really efficient to get the satellites out into space, but they're a lot more complicated to set up. Whereas vertical launches are the rockets pushing the satellite up into space, but that takes a lot of power. So there are fors and against of both of them, but both really good ways to get these little satellites into space. And now I'm going to show you the size of the satellites that we send up into space. Most of the time when we think of sending things into space, we think they're going to go up in really big rockets, but actually the satellites we're sending into space are no bigger than this Rubik's Cube. I know, it's just a Rubik's Cube, it's tiny. Can you imagine this going to space? But actually, this is the perfect size for the satellites we're sending up there. These little satellites might be small, but they do really important things. They monitor things like pollution, climate change, weather, and wildlife migration patterns. Recently, they were able to see that the emperor penguin colonies went up in size, and things like that are really important for us to be able to keep track of. So they're really, really useful, even though they come in a really, really little box. Here at the Observatory Science Centre, we actually have a satellite image showing our local area, which includes the observatory on the map. You can even see the little domes that are at our observatory. Did you know there's actually a light frequency that can't be seen by the human eyes, but can be seen by something called an infrared thermal camera? So we are going to show you one of those now.
Hi, I'm Jerry. Just to say, look, you can see Jen as well. She's now on the screen. What's the benefits in terms of space in using an infrared camera? Well, when you look up at that night sky and see, you can see some fuzzy areas with telescopes. Telescopes look at the visual. They look at the visual side of things. And that obviously means that where there's gas clouds and clouds of dust, things are obscured behind them. An infrared camera allows to look through the gas and through the dust to see that nursery of stars forming behind. So here is a simple example that Jen's going to show of how we can actually look through using an infrared camera to see things hidden behind. So Jen is going to put her hand into this black plastic bag. Now, you can still see her fingers. This is a very simplistic way of showing that infrared the cameras will be able to look through those gas clouds and those dust clouds to see what's behind, giving astronomers more information about things further behind. There we go. In this demonstration, Jen is going to show how mixing hot water with cold water allows us to see the convection currents. This is something that Earth observation satellites can do to look at the jet stream and at the way that the oceans are actually changing and developing. So it's a very useful feature of Earth observation satellites. So here I have a LEGO model of the Rosalind Franklin Mars rover that is due to be launched from the Baikonur Cosmodrome in 2022. There are quite a few missions at the moment on the way to Mars. But this one, which is a lot of UK activity in it, will be leaving in 2022. The Mars rover will be analysing the soil, and as with other Mars rovers, it will have to be autonomous. In the sense it cannot be controlled directly from Earth. The time delay between instructions given from Earth and Mars means it would be impossible to remote control it. It has to be able to overcome obstacles. It has to be able to search for what it's looking for, and using its various tools, it'll be taking photographs and digging into the soil, analysing particles, and maybe even looking for some form of life. The Mars rover that the UK has been heavily involved in is named the Rosalind Franklin after a famous UK scientist who was instrumental in the discovery of DNA. Sadly, she never achieved the Nobel Prize relating to this, as she had died before they were actually awarded to some other scientists. We look forward to the achievements of the UK spaceports when they become fully online. We're sure there will be a number of satellites launched over the coming years which will be used for Earth observation, and the UK will be a reasonably large player in this type of activity. We've talked about the fact that the UK will be launching rockets in the future from our own soil. Let's go outside and launch a rocket from here. For the UK launches, they're either going to be vertical or horizontal. Just to be awkward, we've got one here that's halfway between the two. But basically, it's an air-pumped rocket. The pressure created by this pump will eventually force the rocket off its holder and out the tube. So let's see how we get on. Whoa, not bad. Not bad at all.
The annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.
Alice and Neve here at the Observatory Science Centre. Today we'll be making a constellation viewer. Now Alice will show you what you need to have. So first of all, we need an old kitchen roll tube. You can find this in your household. I'm sure if you ask one of your parents, they'll show you exactly where one is. Now, we also need a black square of paper. This is because we're going to poke some holes in it for later. We also need to print off our favourite constellation. Now, today we've printed off Leo, but you can find this online. Just find a picture of your favourite star constellation, print it off, cut it out, and we'll use it for our activity. Now, for safety, we also have something that will protect us when we stab our holes in our black sheet of paper, which brings us into our next thing. We need a needle to poke our holes into the black sheet of paper. So as you can see, we've already cut out our constellation. So what Alice will now do is she'll poke holes where the stars are onto our black sheet of paper. Be careful though, because the needle is very sharp. Oh my goodness, and I almost forgot, we also need a rubber band to secure our constellation to the kitchen roll tube, which Alice will now show you. Just simply put the rubber band so now when you hold it up to the light, you'll be able to see your favourite constellation, even if it isn't night time. So thank you for joining me and Alice in making this activity. Be sure to visit the Observatory Science Centre, which is now open. All you have to do is book online.
The annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.
Hi, I'm Alice and I'm at the Observatory Science Centre and I'm going to be making a catapult. So what you need is you need 5 of these sticks. You need a spoon, plastic spoon will do, and you need a few rubber bands. So what I'm going to do is I'm going to stack up 4 of these sticks and put them in a little pile. So we've got our 4 sticks and we're going to get a rubber band and we're going to go round like that. So I've got these 4 sticks with a rubber band on the end, and I'm going to put another one at the other end just to make sure it's really secure, like this. Then I'm going to put it down on the table with my other stick like that, and I'm going to get the spoon and put it on top like this. So I hope you can see what I've done. I have these sticks like this with one stick underneath and the spoon on top. And now I'm going to get another rubber band and I'm going to wrap it round the end like this so that it's surrounding both the stick and the spoon. So what I'm going to do is I'm going to take a bit of a rubber band and I'm going to loop it around there. It's going to be quite tight. And then I'm going to wiggle that through there so that there's more stick on this side than on this side. And I'm going to get another bit and I'm going to do the same over here, like that. So now you should have a little cross there with your rubber band. Now that we've got our catapult, we're going to get a ball. The least dangerous is probably a scrunched up bit of paper because we don't want to hit anybody. And we're going to put it in the spoon. We're going to pull this down and we're going to release and it's going to fly away. That didn't really work. Okay, wait, I'm going to shove that in a bit more and see if it does it better this time. Like that. I hope you've had fun making your catapult. Let us know how yours has gone.
The annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.
Hi, I'm Neve and I'm at the Observatory Science Centre. Today we're going to be making flying hoops. Well, so first of all, we've got to make our hoops. Now we need to use scissors for this part, so make sure there's an adult supervising you at all times. So, first, let's make our little one. Now, I'm under a lot of time pressure here, but you can take as much time as you want. As you can see, I'm using scrap paper, which is always best, but it's always great if you can use colours, because we love to have a colourful flying hoop. So let's start with our little hoop. Just simply bring it round into a circle as if you're making a paper chain, grab some sellotape and stick it down. Now this is very fiddly, so you might need an adult to help you with this part, and we do exactly the same for the big hoop. All you have to do is just one bit of sellotape and stick it down. Now we need to stick it to the body. So you can use either a lollipop stick, a plastic spoon, or you can even use an old broken pencil. So all you do is get your two loops and stick it down again. I do not have sellotape. Now that I've found my sellotape, I can stick my loops to the pencil. So simply go under the loop and stick it down to the paper. And do exactly the same to the other side. And then pick it up and you should be able to throw it. Now, we've got to test which one will go further, the old pencil or the paper straw. Let's see. Now, I've got Alice here to help me to see which one will go further. Will it be my eco-friendly pencil one or will it be Alice's one? Now, here at the Observatory Science Centre, it is a little bit windy, but I think my one will still win. Should we give it a go? 3, 2, 1, lift off! As you can see, eco-friendly always wins.
annual Astronomy Festival is our biggest fundraising event of the year. We don't get any external funding for the upkeep of our telescopes and domes, and we really want to keep them in the condition that they really need to be in for you to look through and come and really enjoy the night sky with us. So if you are able to help us and pledge a donation, then there is a crowdfunder link on our website. There is also a donation button on each of the pages on the website as well. Thank you very, very much, and we'd be ever so grateful if you can donate.